Hello everyone, I'm Mrs. Whitaker. Today our objective is to be able to use mathematical thinking to solve for power, current, voltage, and resistance in a parallel circuit. So if you remember, a parallel circuit is just a circuit with more than one path. So a parallel circuit is just a circuit that has more than one path for the current. Okay, so we're going to examine some of the mathematical thinking involved in parallel circuits. So first we have to talk about the junction rule. This is Kirchhoff's first law. We talked about Kirchhoff's second law in series circuits, and now we're going to talk about the first law. So whatever current goes into a circuit must come out. So you have 3 amps that is going in here and 3 amps that's going in here. So there's 5 amps going in and 4 amps going down. That means that 1 more amp is going up this way. So that's 1 amp that goes that way. Okay, so for a parallel circuit, the current that goes in is equal to the current at from one loop plus the current at another loop plus the current at another. So this would be the total current. This would be I, and that's equal to the current here, I1 plus I2 plus I3. So it would all come back around over here, and it would all have the same, it would be the same current as it comes back together. So that's what the total current is equal to. The voltage, though, this is, all the voltages are equal. So when a current enters a junction, you're going to have 9 volts that goes in here. And you're going to end up with 9 volts that goes in here. And 9 that would come down here too. Although these are the junctions. When a current enters a junction, all the parallel branches will start with the same potential difference, the same voltage. So here you'll see this this right here has this potential difference here on the left. On the left can be redrawn this way. So it means that all the voltage is going to be going into these. So all of this 9 volts is going into each of these branches. So, and then it's going to come out again over here. So that's how you can kind of visualize why the voltages are all the same across the different current paths. Okay. So for the resistance, this is a little bit more complicated. Resistors are like doors. If there are more doors, there are fewer bottlenecks. And so if you can think of it like that. So for the total resistance, the equivalent resistance, it's going to be 1 over R. Notice that 1 over. It's not the total R is equal to this. It's the 1 over R. The reciprocal is equal to all of those. So there is a reciprocal button on your calculator. The 1 over X on your calculator. It's your friend. Make sure you know how to use it. So if you have 3 branches have equal resistors, they'll each take about 1/3 of the resistance of the circuit. So that can make your math a little easier if you get that in your as a problem. So then you don't have as much work to do. All right, so in a parallel circuit, the more resistors make current go up because it's easier for the electricity to flow through the different doors rather than only having one door to go through. So here is an example. We have the voltage here of 12 volts, and sometimes it's easy to create this what I call a VERP chart. Whoops. This is a VERP chart. So you can do this for both series and parallel circuits. And it just makes it so that it's nice and easy to keep everything straight. And if you solve this, then you'll be able to answer pretty much any question they throw at you. So here we have we have it broken down by resistor. So the voltage, if you remember, the voltage is going to stay the same. It's 12 volts. So it's going to be 12, 12, 12, and 12. The current, though, that is going to be equal to whatever it is across each branch. So the total current is equal to I1 plus I2 plus I3. And so that means that we have V equals IR, and we have V and we have R, 12 and 30. So it's V divided by R is equal to current 1. So it would be the 12 divided by 30, and that's equal to 0.4. This is 0.4 amperes. We can also get this by looking at the current total. Well, actually, we haven't done this yet. So, but we know that these are equivalent because it's 0.4 and 0.4, just because the resistors are all the same resistance. So then if we want the total current, we just add these up, and that's going to be 1.2 amperes. So then we want the equivalent resistance. So here it's going to be 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So it's going to be 1 over 30 plus 1 over 30 plus 1 over 30 is equal to 0.1, but that's going to be 1 over 0.1, which is equal to 10 ohms. Okay, so then this becomes 10 right here. And then power is just V times I. You could use the resistance one as well, but that's the first one, and it's pretty simple, so we'll do that. So it's 12 times 0.4, and that's 4.8 watts. So then this is 4.8, and this is 4.8. And this right here is going to be 14.4 because it's 12 times 1.2. So that's equal to 14.4 watts. Okay. So then to actually answer this question, it says, what is the resistance for the entire circuit? That's just our equivalent. And we can go to our VERP chart and read it. So then that's going to be 10 ohms. What is the combined resistance for the bottom two loops together? So this is right here. So just the R equivalent of loop 2 and 3 is equal to 1 over 30 plus 1 over 30. And we're going to get, is going to be equal to 14.9 ohms, I think. Okay, so that's 14.9 ohms, and you can notice that as there are fewer resistors, the resistance actually goes up. Okay, so this is an example of the VERP chart, and you can do this to break it down for a series circuit as well, and it helps you find out what each of these are. Now, what would the current be here? The current at this rate, it hasn't gone through any junctions yet, so the current is going to be the total current. So it's going to be, each of these ammeters are, it's going to be, this first one is equal to 1.2 amperes, and then it's going to come in here, and it's going to be 0.4 amps. This is equal to 0.4 amperes. This is equal to 0.4 amperes. And when it comes into here, it's going to split here and here, and you're going to end up with the amount that's going to go into here, and you're going to get 0.4 that goes here and 0.4 that goes here. So then this is going to be equal to 0.8 amperes, and then they all come back around here, and it goes back to 1.2 amperes here.